Hi,
Okay.
everybody. And I got some stuff on my screen. Okay, so today I'm going to do, it's kind of a broad talk. I know I have a broad audience, I think, so I'm going to do sort of a broad introduction and try to get into some details and then try to get into, an example of deep learning with convolution networks and then talk about how we run this on HPC. And it's going to be a lot of stuff I got packed in here. It's usually a longer talk. We usually do these workshops with what I'm going to do today is usually includes tutorials and maybe some demos that we run for a longer. So this will be some parts I hope I'll try to go through quickly, and if it's too quickly, let me know. All right. So just my quick outline. I'm going to do an overview, talk about neural networks, or originally they've been called multi-layer perceptrons, convolution neural networks, and talk a little bit about how they work when they're scaling. I probably won't do the demo, but I will show what a demo looks like for a convolution network classification problem, and then talk about the practical considerations, some of the guidelines when we run this. What do we do for hyperparameter searching, setting up workflows, and so forth. All right, I always like to start my neural network explanation with logistic regression. I think that's because a lot of people maybe come from different fields where they've been taught some linear regression models and maybe some linear logistic regression. So I always like to start with, well, this is what the logistic function looks like. And here it is for a couple, just, there's a couple parameters when we're talking about a function of just y equals f of x. And these two parameters can shift this function around, so it can look very different. If you increase the weight, it can be looking more like a step function, and that could be shifted around the x-axis. And with different combinations of parameters, you can get all kinds of different looking functions. And if we start combining these, so here I have one input and two units, and each unit is a function, and they might have different parameters. They have different shapes, and if we add them together, we're going to get something more interesting. So if we do, in this case, we add them together, and these two original functions are shifted over a little bit, and so now we get a bump function. It peaks at a certain value of x1. And we can play this game, and you can build all kinds of complicated functions. So just by playing around with those parameters. And what this points to is the fact that um, multi-layer networks can represent any logical or real valued function. So in that sense, they're unbiased. They have the potential to overfit. They have potential to fit anything. That doesn't mean they're going to always easily learn, but the representational power is there. And so once we, are comfortable with the logistic function, we can sort of draw this out as a little graph. Here I've drawn it out with an input line. There's a weight and a bias unit. And these names come out of the fact that, they're sort of biologically inspired. Um, so they're basically the same as linear regression parameters. And when we draw the node, the unit, and we talk about it's making a transformation from an input to output, and we call it the activation function. And we often don't draw the fact that when the lines converge, it's usually a summation. So we're taking a summation, producing an incoming sum for the activation function. And of course, we could write this out as dot products. And when we have an extra unit that's for output, we'll call that an output unit, and then the intermediate units we'll call hidden units. And if we're smart about how we index our parameters, in this case our weight parameters, we can all set this up as just a matrix operation. So this is typically people use an indexing scheme of to and from, and you have a weight matrix, and you multiply it by your input. So more generally, we can add hidden layer. We can have many inputs. We can have many outputs. A multi-layer perceptron, we typically mean one input, one hidden layer, one output. This was the basic neural network that people started with years ago. And we have an input, and there's many, if it's coming from a data matrix, we'll have some, one equals 1 to n observations, and maybe a p vector for every input vector. And we might have some number of output units. It doesn't have to be 1 to 1. It could be many to 1. It could be many to many. We'll have some number of hidden units, and each line represents a weight parameter. And so we can make this even more general and talk about the fact that we have many layers. The operations we're doing here, we're going to take some input, and we're going to do a forward propagation. That means we're going to apply the input to the input layer, layer 1. We're going to calculate activations for layer 2, calculate the outputs for layer 2, and so forth and so on. So we're doing a forward propagation. And when we get to our output, we're going to have some label. It's going to be a supervised learning problem typically. And we'll have some error information, so we can back propagate that error information. And the way we back propagate is using derivatives and the chain rule. And I'm not going to go into the details of the chain rule, but it's essentially saying the chain, the change in error as a function of your weight depends on everything in between. And as you go farther back, though, the information gets diluted and the error gradient starts vanishing. We call this the vanishing gradient problem. And so this was a problem for a while, for many years maybe, and after some trial and errors, people figured out that there's a certain kind of activation function. Instead of using logistic, we could use this other activation function called the rectified linear unit, and it has a large linear. It's linear for a big part of its for half its domain. So it actually helps solve the vanishing gradient problem because the gradients there's no saturation when it's active. So that was one thing that helped build networks with deeper, more layers. So the algorithm, once we comfortable with what forward propagation and backward propagation is doing, and if we're comfortable with what machine learning algorithms look like, it's easy to write down this algorithm. It's we initialize our weights to some small value. We have a loop. We're doing forward propagation, backward propagation, and then we update weights. And typically this is like a version of stochastic gradient descent. And what's interesting, we do this for a batch of inputs. We don't do this for one input at a time. We'll do this for a set of inputs. And maybe it's all the inputs at once. But typically you might have a memory issue if you have a lot of data. So you do it for a batch, some subset of all your data. And there's some learning rate and there's some optimizers, and everything kind of works towards like optimization problems. And you stop typically when our validation error reaches a minimum, or maybe we just have a maximum number of epochs, or both. Okay, so neural networks, the main things we have to choose is setting up an architecture. That's typically your number of hidden units, your number of layers. As we get into more dealing with unstructured data, we're going to have special layers. Optimizer and your learning rate. Your loss function is probably going to depend on your task. If you're building, doing classification or doing regression, you're either going to use some sort of error maybe or some kind of entropy. If you have particular other tasks, you can build custom loss functions, which are combinations of things. And in general, the more hidden layers, the more hidden units, those are our resources. That's what creates the complexity of the neural network. And that also means you have more potential for overfitting. Whoops. Okay. So in summary, our neural networks are in general, they're flexible, they're powerful learners. Hidden layers are doing some kind of nonlinear transformation of the input. But now the bad side is that it takes lots of parameters. Sometimes it's hard to interpret, and typically compared to other machine learning models, you need more data. But if you have your data, you can do a lot of useful things. So a neural network can discover visual features using a convolution. So, and we'll talk about the convolution layer next. So imagine we're doing an image classification of digits. So here is the hello world problem of deep learning. Imagine we have this database called the MNIST database, and there's a bunch of handwritten digits. It comes from postal codes. It's been around a while, and people have been experimenting with this for a long time. And the issue is, how do you classify digits? So image problems, typically they used to start with something like this. Well, let's say so I've got a picture of the number 7 here where I've scaled everything to between 0 and 10. And I'm going to look at little patches. So I'm going to look at a 3x3 patch, patch of the image. I'm looking at near the tip of the 7, so I've kind of zoomed in here. And I'm going to multiply it by a matrix, which is also 3x3. And we can think of this as a filter or a template, like we're trying to match a template. And so this particular matrix is looking for a combination of values where it's small. As you go left to right, it goes from small numbers to larger numbers. We can call this our weight matrix, for example. And we're going to multiply it element-wise times our little patch, and then we're going to put the sum into this new window, this new output map. And then we're going to slide our patch. We're going to repeat the operation. We're going to put the sum in a new cell of the output map. And we're going to keep going like this. Sliding the filter is known as a convolution operation. You're sliding and a filter over something and doing addition operations. And so we're creating a new output map. And it's going to look something like this. And the highest values in this output are essentially representing some kind of feature, which in our case is something that matches the template. And we might even go one step further and say, we can do a maximization over little windows. So this is called a max pooling operation. It helps downsize the sample. And at the end, our little patch here, we started out with a 5x6 patch. I've transformed it into a 2x3 feature map that represents an edge gradient. So that's a basic operation of a convolution. And people have been doing this for a while. But the problem is we had to come up with those gradients. We had to come up with that filter. We were feature engineering in this case. But we'd like to do feature discovery. It's kind of hard to know what features you always want to have in some image processing or classification task. So if we think of this as weight parameters, a convolution layer is a set of feature maps where each input map is derived from the convolution. And in neural networks, we're going to learn these parameters. So the convolution operation is introducing some more hyperparameters that we have to think about, the size of the filter. And in general, smaller filters are better. And in fact, people have found that, if it's really good to just start with a 3x3. It's kind of like the smallest filter you can and just build layers. The number of pixels to slide over, usually slide over 1 or 2. As long as you have computational power, you can pretty much do 3x3 filters and slide over 1 pixel at a time, and then you don't lose any granularity. People typically do a max pooling. It helps to downsize your feature maps. But now the number of filters is now a new parameter where it depends on the task. It's not obvious how many filters you should have. So we'll get a feel for that when we go to talk more about this example. So let's think about how this scales up. So imagine I have not a black and white image, but now I have a color image. And we would crop it to a certain size. Like in this example, it's a 224 height, 224 width by 3 for the channels. And so a filter we have, if I build a 3x3 filter in height and width, I also have to take into account the depth. So in this case, because I have 3 channels, I'm going to have a 3x3x3 filter. So my feature map output is going to depend on the filter size and the slide parameter. So I'm usually dropping off some of the pixels on the edges. Sometimes people do a padding, and so you don't have to make a smaller map, but typically we're downsizing as we go along. And we repeat this for many filters. And each filter is a 3x3, and at the end you stack all the output feature maps, and so you end up with a convolution layer. The thickness of the layer is the number of feature maps. Sometimes it's called channels or number of filters, or we just might call it depth. And then we're going to add another convolution layer, and that filter size is going to be a height and a width times the number of filters of the previous layer. Or we might add a layer of max pooling to downsample. And we could continue this operation and sort of do this and build up a larger network, a set of convolution layers And as we go from left to right, we are downsizing, so we're getting smaller and smaller feature maps, but we're also increasing the number of filters, so we're producing more and more feature maps. Okay, and then at the end, and then our last layers is going to be the classification part. And this looks like a multi-layer perceptron. In this case, it's got two layers, two hidden unit layers, one output layer. This was an example from the Vision, I can't remember the name of the conference, ISLVR conference, where they predict 1,000 object classes, and it's a big classification problem. And so this was the kind of networks and the kind of work that was being done that really advanced the field. So what do these convolution layers look like? Well, here's some of the first layer of that previous network. And you can see that these are the filters. So these are basically the weights. And I can't remember the size of these filters, but if you look at them, they kind of look like maybe they're doing some kind of edge detection, because there are patterns of higher values or lower values and higher values. But they're in different orientations, and then some of the filters look like patches of color. So it's hard to say exactly what these filters are doing or why they're at certain angles. But presumably these are low-level features of the 1,000 kinds of objects that they're trying to classify. And if we look at the activations, so here's a picture of a car. As you go from left to right, you're going from the lower layers up to the higher layers. As we go from left to right, we see that the activations are still kind of looking like the car, except certain features are highlighted. Maybe it's an edge, maybe it's the front, maybe it's a part of a wheel. Who knows? It's hard to say. As you go from left to right, also the feature maps are getting smaller. And so these features are thought to represent something more abstract about a car. So we're losing, spatial resolution, but hopefully we're gaining conceptual or class information. And in this example, the final output predictions is strong prediction for car, a little bit of truck, airplane, ship, and for some reason horse. Okay. So the summary here is that convolution networks work because the layers, our layers are essentially a special architecture. They're essentially built to pull out features from an image. They're essentially biasing the kind of thing a network can learn. The lower layers have, typically less filters. They represent simple local features that are presumably relevant for all classes. And you could do, people have done more in-depth examination of what these features look like. For example, higher layers have more filters that cover larger regions, and they represent, something presumably about an object. So now we can also say a little bit about what deep learning is. Deep learning really refers to learning complex and varied transformations of the input. That's one way to think of it. Deep learning refers to discovering features of the input. And this is, I like to think of it this way, especially because one of the successes of deep learning networks is dealing with unstructured data, raw text, a bunch of images, sound, audio sound. And so it's really pulling out features for us. We don't have to pre-process the image. We don't have to be engineers to, take an image and create our own features. Practically speaking, for a lot of people, deep learning is just a neural network with many layers. And in that sense, it's, building up these transformations and maybe doing like, a hierarchy of features. So sometimes people talk about it in that sense. Okay, so I wanted to do, so you typically do a network demo, but because this is an hour long, I'm just going to give you some slides of what it looks like when we do this digit classification. So again, here's the set of, the kind of data we have. We're going to use the Keras the Keras package, which is part of TensorFlow, which is the Google module, the Google library for doing fast computations, and it's a Python-based library. On Expanse, for example, so this is our local HPC system, which is part of the part of the NSF um, the NSF set of HPC systems for research and support. And we have an interface to run a Jupyter notebook. It's our Expanse portal. If you go to the Expanse website, it'll have a link for the portal. When you go into the portal, it'll ask you to log in, and then it'll ask if you want to run interactive applications. So here I've selected Jupyter, and depending on your account information, depending on what you want to run, you can run on a GPU interactively, or you can run on a compute node interactively, which is a CPU. You can use different partitions. So I have an example here of the kind of thing you're going to want to enter. We typically, this was done for a workshop, so you wouldn't have a reservation, but this other information is pretty much the kind of thing you want. And there's more details about this on the website. By the way, I tried this just before our session, but apparently there's some work going on in Expanse, so it's actually not working at the moment. So I can't show you a live demo. But here's what it looks like. Basically, we're running a Jupyter notebook interactively with the Expanse HPC system. You want to find where your Python notebooks are. Here I'm showing a bunch of notebooks. If anybody wants to get these notebooks, I believe we have these accessible from a GitHub repo. These are notebooks I did for our workshop last summer. And in the notebook, there's, it's a typical Python code. There's pre-processing data, loading data, pre-processing data. And the heart of the code for a convolution network is this Keras code where we build a model. So Keras has these tools or these functions to help us build a model. The sequential model is kind of the straightforward feed, one layer feeds into the next layer model. There's other kinds of ways to build more flexible models called the functional API. This is using the sequential API. I declare a model, I add a layer. In this case, I'm adding a convolution layer. I'm giving it information about the filter and the stride and the activation, the input shape. And in this example, I'm adding a max pooling layer, or maybe I would add another convolution layer. When we go from our convolution layers to our classification layers, we have to do a transformation, and this would be called a flatten in Keras. So we're taking our little maps at the end and for little maps at our last convolution layer, and we're transforming this into a vector. So the nice thing about Keras is you can build these sequence of layers, and these layers are functions, and some of these are actual like hidden layer functions with parameters, and some of these are just functions like the flatten operation. And finally, I have these classification layers, and these are called dense layers in Keras. And of course, my last output, because I have 10 digits, we use a softmax output activation, and that is accompanied with a categorical cross entropy loss function. So if you're not familiar with the softmax from things like logistic regression or cross entropy terms, the Keras APIs and the Keras has good the Keras documentation has good tutorials that will explain some of this. The last line here, I have an optimizer. I like to use the Atom optimizer. Other people like stochastic gradient descent with a adaptive learning rate. Those are two that I see are used the most, but there's other ones. And it's hard to know which one is better, but we'll talk a little bit more about that. Okay, and the thing to remember about the way Keras does it is, every layer has some input output. And it's not obvious when you're doing this, what is the input output shape? Keras will try to figure it out. So I'm not actually saying, when I talk about the max pool layer, I'm just, saying add this layer. I'm not telling it what the output shape is going to be. Only with the last layer, the dense layers, I'm telling it this is the number of hidden units. So you're going to have 32 units as output. Okay. Okay, and this is the convolution layer. As I said before, just zoomed in a little bit. This is what the parameters look like. And And if you run this, if you train a network on this data, if you look at that demo, you're going to get something like this. If you in that particular notebook I have, I am plotting on the left 3x3 filters. So I ran this network with 3x3 filters, 16 of them. So these are 16 3x3 filters. And you look at this filter, it's not obvious what these filters are doing. But here's the activation function, the activation output for those 16 filters. These, remember, the first convolution layer. And again, it's taken the input of a 5 and it's done some transformation. Some of this is not doing much of a transformation. Some of this is doing a really kind of suggestive transformation. So this bottom left is looking like it's highlighting maybe part of the edge of the middle part of a 5. And if we look at that filter, there is a white square in the upper right and then darker squares below. So this filter, what would match this filter? Exactly this kind of edge. Okay, I hope that sort of makes intuitive sense. And so it's hard to know what all these filters are doing, hard to know what all these transformations are doing, but sometimes you can sort of, you know, get some sense about it. But what if we change the filter size? So here I said, let's use a 9x9 as the first convolution layer. So instead of 3x3, where I'm looking for granular stuff, now I'm looking for 9x9 stuff. So the output, or the filters themselves, again, hard to interpret. It's tempting to say, oh, it's looking for an edge this direction, looking for an edge that direction. Certainly, if we look at these transformations, you know, it's very suggestive, like it's trying to highlight some section of a 5. Instead of just an edge, now it's an entire line segment with a certain thickness. So as you get to larger filter sizes, you're looking at, presumably and intuitively, and we can see it to some extent, larger features. I hope that makes a little bit of sense. Because really, you know, you can spend a lot of time thinking about what these convolution layers are doing. Obviously, with the large networks, it's you know, people do spend some time trying to interpret those things. Okay, so that's the basic convolution network. You know, nowadays there's all kinds of deep learning models for specific kind of tasks. You know, the success of deep learning models are handling unstructured data, and so you're going to have similar kinds of, you know, conceptually strategies to when you're building a network, whether it's a vision network or a sequence network, or, you know, these large language models. There's some feature processing going on in the lower layers, and you know, maybe some classification at the output layers, or some other tasks. All right, so let me switch to like some guidelines of how you might run this on HPC, or how you might run these in general. Okay, so these are like things to think about in your project. So the first thing really is choosing hyperparameters. As I said before, layers. There's the architecture hyperparameter. We'll talk a little bit about that. The basic idea is you're going to do a little bit of exploration and exploitation, if you're familiar with those terms. You need to figure out an efficient job workflow. That's something that's really, you know, in some sense it's your personal preference. Sometimes you got to look at what other people have done. Sometimes the CPU works fine for a lot of cases, especially if you're using with small data and you want to just test things. If you're taking a pre-trained model, sometimes you can just run those on a CPU if you're not training, but you just want to run the calculations and test it with different data. You're definitely going to want to use GPUs for large models or large data sets, but then you have to just be careful about the memory trade-offs. You know, you can do model saving in Checkpoint. That's all fine in TensorFlow. TensorBoard is a tool that helps you monitor your performance as it's running, and we do have that set up to run on Expanse, but there's some but to run it securely, we have to run it. You can't just run it directly. So we do have a procedure to do that, and I don't have it. I don't have a slide for it. But if you want to use TensorBoard, we can set that up. I find that it's not necessary for me. Like, I don't particularly get much out of TensorBoard, but I do. But on a GPU, if you're trying to debug certain things on a GPU or get it more efficiently, then TensorBoard has some tools that could be nice. Oops, did I skip that? Okay. All right, let's talk about juicing hyperparameters. So in general, we have architectural related hyperparameters, algorithm related hyperparameters, other parameters that help you just learn more efficiently. I'm not going to talk about all these, but when you're building your network, just try to keep in mind what are the things, some of these things you probably want to look at what other people did, and really everything you want to look at how other people have set this up. Um, some options are sort of determined by the task, like your loss function if you're doing classification versus regression. And again, use what works. See if you can find related work from other from papers and so forth. So another note about hyperparameters. So it can take a long time. This is where you could get stuck finding good set of parameters. It's hard to find a global optimum. So if that's if you're trying to squeeze out, unless you're doing a competition, squeezing out very small incremental improvements, maybe that's not the most important thing. I always get to try to start with small data to get a sense of what good parameter values are. Sometimes it's good to start with small data. Make sure you have a network that can at least overfit. If you have trouble running a network and you feel like it's not learning anything, it's just producing like random output, try to do a little bit smaller data set and just make sure you have enough resources and at least see if you can overfit. So I had a case just a few weeks ago. I had mislabeled my output and the network was like learning nothing. It was just producing random output. So I made a smaller data set. At least I should make sure I can overfit the training data. And sure enough, I could learn the training data, but still it generalized to my validation data just with random guessing. So that told me, okay, maybe I had either, I didn't think the problem was so complicated. So that suggests, so then I was able to go figure out I had some data problem. Okay. And the easy thing to do with hyperparameter search is to do a grid search. Tick out spaced values like, 1 layer, 2 layer, 4 layers, 8 layers, for example, if you're doing multi-layer perceptron stuff, or even if you're doing convolution stuff, figure out a way to space out your hyperparameter values. And when I say exploration versus exploitation, what I mean is, if you start with a small data set, you get a good idea what kind of parameters work, and then you could do a grid search, and then you could say, well, look, I have good values here and maybe some good combination of values here. I'm going to focus in on those values and do maybe a more focused grid search. There is a tool called, Keras has a tool called, we're looking at the next slide, Hyperband. And it's a tuner, it has some tuner functions that help with the wide search. Okay, so it's called Hypertuner, sorry, not Hyperband. And so this implements several strategies. Hyperband is one of the strategies, and that's like running a little tournament, so you can have a lot of configurations of hyperparameters, and it'll help you weed out which ones to focus on. It'll sort of, I'll show you what that looks like in a second. A random search, I haven't used the Bayesian optimization, but this one is like doing kind of a function approximation. So it's looking at combinations of hyperparameters where it hasn't searched before, and it'll like put together combinations for you. But let me show you what the Hyperband one looks like. So it sort of sets up a tournament, and each round it's going to take some network configurations for a small number of models. I'm sorry, a small number of epochs. And then it's going to run, let's say, the first round with, here I have like 8 networks in round 1 for just a few epochs. And then round 2, it's going to run less networks, but for longer epochs. And round 3 it's weeding out the networks. So now it's only like 4 maybe networks at round 3. And then round 4, it's only, the last 2 networks and one of them is a winner. So it's almost like setting up a tournament, but it's not going all the way with all the number of epochs. So you have to set up the parameters so it can set up this little tournament. And just to give you a feel for what that looks like, if you have some code and you're doing some model and you have it's a good idea to make your model a function, have a build model function. And in this build model function, you have your parameter choices. Maybe it's an activation choice, maybe it's a number of filters. And these are your hyperparameters. And then to run this with the tuner, you're going to surround that. You're going to have another build model function that wraps around your first one with your hyperparameter, your hyper tuner parameters. So this is basically your choice information. So you're going to say, okay, my number of filters are going to go between 8 and 32. And then you have a tuner object in which you are telling this hyperband function to use the wrapper build model. Use the wrapper build model, and then all these other parameters are like your fit function parameters. So this way, their hyperband function can create this tournament. Just let me say, so I find it's kind of useful to help me do a wide search to do something like this, but in the end, I always like, once I find a good set of parameters, I'll end up doing a grid search in a smaller, into a smaller set. What about workflow? So I think the typical workflow you're gonna probably want to do is, you're gonna have a job, and for each job you're gonna run some model, and each model you're gonna loop through maybe cross-validation data sets, maybe a couple different, just maybe not a full cross-validation, but like training validation tests with a few parameters. So this is the typical kind of thing. If you had like super large data, maybe you would just load the data in the memory and then run a bunch of models. So you could imagine situations where these last two levels are reversed. So you have to sort of consider how long a model runs for one configuration of hyperparameters for one data set. And you want to organize your jobs into reasonable chunks of work. And of course, if you have large models or large jobs, you ought to consider model checkpoints. Configurations of models. So we're talking about configurations of hyperparameters, and somehow you want to set that up so your model is, you can sort of set that up. You want to set it up so that at the job level, you can easily change what those configurations look like. And that could be done through arguments in Python. Python has this nice tool to handle arguments. A lot of people like to use YAML files. So here's what it looks like to use a YAML file. It's basically a text file with some parameters and values. And you basically load that text file, and you can extract the particular parameters in the text file for your parameters in the program. So it's like reading a dictionary. And that's kind of nice because it's a text file. You can run your job, you save the text file, you can modify a text file, and just make sure you keep track of stuff there. On something like Expanse, you could, if you have a text file, you could actually in your job just have statements to set up those parameters. So every time you run a job, everything could be right in your job script. So here's an example I was sort of playing around with. So sometimes people like it this way. I don't know. It's sort of your personal preference. Okay, so I've been talking about Python notebooks in our demos, but when you run this after a while, you kind of get, really don't want to always have a notebook. Maybe you do. If you want to keep things in a notebook, you can, and then you can use a Jupyter convert command, and right there in your job script, for example, you could convert it to a script. Convert your Python notebook into a script, and then run your script. The only thing you have to do is be careful to turn off your plot displays. Maybe save your plots in a file, and then set up your, have some good way to set up your parameters. Papermill is another tool that people use. It takes a little bit of other programming to wrap your output, your plots a certain way, and a couple other things. So that's another option if you want to do that. If you're doing this over and over again, maybe you just take your notebook and put it in a Python script, and that's probably what most people do. Let's talk a little about GPU nodes. Okay, oops, sorry about that. There we are. Okay, so if you're not familiar with GPU, the GPU has typically a GPU node has multiple devices. Now, by default, TensorFlow will run, if it's running on a GPU, it's going to look and see if there's a GPU, and it has these commands. In fact, I have a little snippet of code that shows you the kind of commands TensorFlow has to look and see if it's, if there's a GPU device. So if there's a GPU device, it'll run on the first GPU device, or the 0th, if there's a GPU. Otherwise, it'll use your CPU cores. And remember, this is all those dot products that we saw in the forward propagation and back propagation steps. That's really what it's going to be using the GPU for. Okay. In general, so here's a little test I did. In general, your GPU is always going to be faster. So this was a test where I had a multi-layer perceptron with 4 to 12 layers, 512 to 1,000 hidden units, and the GPU, the time it takes to process 25 epochs, for example, in this with this data set, the GPU is just a linear increase, whereas the CPU, it starts to have a nonlinear increase after you get up into the 12th layer. So these are not terribly large networks. It's not that you can't run in the CPU, but you're waiting longer. So eventually, so in this example, when I had more data, it was just like I'm waiting a long time. The downside for GPU is that there's less GPUs on our HPC systems, and so you might be waiting in the queue more. So that's the trade-off you have. Okay. Let's talk about the parallelization on a GPU node. Let's see what that looks like. So the main approach to parallelize your training is called the data parallel approach. In this scheme, you take your data, you split it up. So we're making our data into, let's say, if we're going to run on whatever number of devices, we can split up our data in those number of devices. And we're going to launch our Python script, our neural network script, on each device. And each device is going to train, they have the same model. They train a copy of the model with their part of the data. And then those parameter updates have to be aggregated and broadcast for across those model instances. So somehow there has to be a procedure so that the model parameters are kept the same, but each model on each device is running with a separate piece of data. So that's the main idea of data parallel. Keras has a library or a tool that's called a strategy, and there's some functions to help you define the strategy. There's another tool called Horovod, which uses NPI as a wrapper, or wraps around some of your functions to handle this stuff. So that's for the data parallel. There's another approach called model parallel. So if maybe you have a really large model, you could in principle split the model, and each part of a model is running on a device. And maybe it's processing all the data, or maybe you have a combination of model and data parallelism. So these last two approaches, I haven't actually used these last two approaches. I know with the large, like the GPT model, now there's a tool called DeepSpeed, and that's supposed to help you set up a model data parallel implementation for parallelizing the GPT training, for example. Another thing you can do, another issue that comes up is memory, because the GPU doesn't have as much memory as a CPU system. So you can do things like using mixed precision. You sort of have to, it's not that hard to set up, but you have to kind of make sure you're not losing accuracy. So typically we might do mixed precision for hidden layers, but maybe not the output layer, for example. All right, so let's talk about, as I said, the data parallel is the most common approach. So let's talk about this some more. So in Keras and TensorFlow, if you're running on a single GPU node, so a single GPU node is going to have several devices, you can set up what's called a mirror strategy. And so there's a distribute library or distribute module, and there's a mirrored strategy function, and you tell it, let's mirror my model on these GPU devices. So on Expanse, for example, our GPUs have our GPU node has 4 devices, 4 GPU devices. So you tell Keras, okay, I'm going to use a mirrored strategy, and when you build a model, you build it inside the scope of a mirrored strategy. So Keras knows, like, okay, this is a model that's going to be built, and I'm going to copy this into all the devices. So your build model, so basically your build model is copied. And then you just train as normal. And when you do training, whether you're using GPU or CPU, well, for sure when you're using GPU, you want to try to do things in batches of 32 or at least evenly the numbers that divide into 32, like 248, for example, 248, 16. And that's because GPUs vectorize things into sizes of 32. So always try to, it always runs a little bit better if you use, something that could be divided into 32. So the mirror strategy with multiple devices on one GPU, that's pretty straightforward. But what if you have a bigger problem and you want to use multi-node? So this is now a little bit more complicated. Keras has a multi-worker strategy, but it requires setting up config files with IP address. So if you're on a static machine, you always know what the IP address is. You could use the multi-worker strategy. It has a concept of a chief and a bunch of workers, and you have to just say, okay, this IP address is your chief here, and everybody knows what the other IP addresses are. Every device you're running on. But on our HPC systems, resources are shared. That means your IP addresses are dynamic. It's not that easy to set up. You could set up a multi-worker strategy, but you have to go through, you have to go and pick out Slurm information, and it's a little bit tricky. But it's a lot easier to use Horovod. So Horovod sets up some wrappers in your code and handles the MPI for you. So you would do this in a Slurm batch job, and that's what I want to show next. So on Expanse, for example, if you're running single node, single device, we are typically using Singularity containers. So there's going to be a Singularity command in your batch script, and that's going to run your Python script. Again, your Python script, like your typical Python scripts, load data, build data, train. With MPI, we're going to perform first to the MPI run command, give it the number of tasks. So the number of tasks is going to be, if you're running on one GPU node, it could be 4. It doesn't have to be 4, it could be 2. If you're running 2 GPU nodes, it would be 8, for example. So we run an MPI run command, and that launches the Singularity command, which is going to run the Python script. And so this Python script gets with the Singularity container gets distributed across nodes by your MPI and your Slurm job. Now, what Horovod is doing is essentially this: you have to initialize the backend communication. So you're initializing. If you're familiar with MPI, you're initializing the communication stuff, and you have MPI rank information in your script, in your program. Then you're gonna, after you load the data, you're gonna do some sharding or splitting, or maybe you're smart. Maybe you have procedures to load the data so it's already split up, for example. So you could do that with rank information. You could do that with TensorFlow dataset module. You could do that with NumPy if you have the data set up the right way. And then you're going to set up a distributed optimizer. And so again, this is going to be a Horovod function, and it's going to have, in part of your model, it's going to, instead of having a regular optimizer, it's going to basically wrap around that optimizer with some distributed optimizer. And then in your training, there's going to be a batch aggregate. So after each batch processed, there's going to be some aggregation of your weight updates, and there has to be some kind of way to let every model knows what those weight updates are. So typically your zero rank process is handling these weight updates, and it would also, in your zero rank process, you're going to handle checkpoints. So only one of your model instances should be doing checkpoints. All right, and just to be clear, so the MPI run command says launch this number of tasks. Each task is running on a different device, but as far as those programs know, they're all running on GPU device 0. So there's a little bit of, but at least that's how it works on Expanse. It may not be that way in other systems, I'm not sure. And so you have a bunch of instances of your script, but they all have different, they all know what their piece is because they have different rank information. And then during training, there's going to be some all reduce, which is going to do the aggregation of weight updates, and there's going to be some broadcast, which shares the information about what the new weight values are. And so in general, bigger batch sizes are better because then you don't have to do this communication as much. But a bigger batch size also means that you're going to be using more memory. Okay, so just to give you a sense of what the code looks like, it's actually not that, it's actually pretty straightforward. I got this, you can go to the Horovod website, and the example I have there pretty much works as is. I don't think I did anything particularly different in my tests and when I've used Horovod on other systems. And it goes something like this. So the communication, you have to initialize your rank. It's just an init statement. You sharing and splitting data is probably the most confusing thing because it really depends on what your data looks like that you have. You could use a TensorFlow dataset module API, but you can also use NumPy. But it depends on how much you have to read in and when, if it's split already. It depends on whether or not you have a lot of files of images and you want to use a TensorFlow dataset as a generator, for example. So those are all the issues you have to sort of work through. The distributed optimizer, just one line of code, say, Horovod, distribute your optimizer. You tell it what the optimizer is. And then there's some adjustment. You want to make, it's recommended you make some adjustment to your learning rate to handle the fact that, you splitting up your data. And then the batch updates and the aggregation and the broadcasting of the weights, they're actually handled for you. All you got to do is, you do a normal model compile. That's normal Keras statement, but you have this other option. And experimental run TensorFlow function. Okay, so this just basically tells Keras to make sure it uses this distributed optimizer. That's a little bit of, I'm probably mischaracterizing that a little bit, but the website explains that a little bit more. Okay, so that's it. And when you're running on a GPU, oops, sorry. This is almost my last slide. Okay, and when you're running a GPU node, you can always SSH into that node, or it's a CPU node, you can SSH into that node. You can see what's running using the top command on a CPU node. If you are running on a GPU device, you can SSH into those nodes and run the NVIDIA SMI command, and it's going to show you how much memory is getting used and what kind of what kind of usage you have on the GPU devices. So I'm only showing you part of the output from a NVIDIA-SMI command. So that's something else you could do when you're debugging, when you're monitoring these things. One of your issues is going to be, am I running out of memory, for example, and you can look at that. Okay, so where do you go from here? I always tell people, start with relevant examples. TensorFlow has pretty good tutorials. A lot of the blogs you see, they basically take the TensorFlow tutorials, they run it, they modify a little bit, and they put it on their blog. So I like to go to TensorFlow for a lot of, to start with a lot of things. Sometimes they don't have great explanations, but sometimes, they do. I find they're pretty good. All right, and that's it.